越老，我跟你讲，一般比较老那些就50、就7、8年。
但是你看他这是2019年，那个他妈的那个简单，那个简单。那个叫难度一样。
你好过你Midterm吗？
他那个他那个很惊讶吧？他那个超级牛逼了，他那个就这么简单。就是说，
我之前最低的那个Midterm拿了4，开了10。然后呢，我40分考不好，然后呢，就是那个考嘛，看大家那个评分太低了，好吧？变成30多到10，对，然后我就直接把我在Midterm里面，就我在final做找嘛，做就我要把我们点分就上到决赛。
All right. So why don't you get started by, brushing all that reading week you forgot all of CS135 off, and see if you can implement this function, which is a combination of simple recursion and structures. So take a few minutes and see if you can get it. Yeah. Nope. All right. So you've had a few minutes to think about this particular example here, and instead of asking one of you to solve it, what I'm going to do is I'm going to open up Bracket, and we'll actually solve it here together. So let's go file. So first off, of course, we need to put that structure definition in here. So there we go. Now, something to remember is when you use this define struct, Racket is going to give you a bunch of functions automatically, and they're super useful. So you're going to get a constructor to help you build this structure. You're also going to get a predicate so that you can check if something is an UNO card or not an UNO card, or whatever structure type you're using. You're also going to get a number of selectors or accessors, which are functions that are responsible for giving you the value of a particular field. So you get those automatically. So in this particular function, what we want to do is actually, given a hand of these UNO cards, I want to know, and a color and a value, I want to know if I have any playable cards. If you're wondering why did I pick UNO cards, it's because my daughter likes UNO. It was on my mind. So we're going to start with, we'll call it Playable Card. And it takes a list of these UNO cards, and it's going to take a color and a value. And what I need to do is I need to check each card in the list, and the first time I find a card that has either the same color or the same value, I produce true. Otherwise, if I make it through the entire list of cards and I find no cards that have the same number or the same color, we should produce false. So this is going to be done with simple recursion. It's not to say you can't do this with a cumulative recursion. It's just that a cumulative isn't quite appropriate for this particular question. So our base case, of course, is if the list of cards is empty. If we've managed to get to the end of the list of cards and we haven't found anything, that means that it doesn't exist. So we're going to produce false. Now, I'm going to check to see for a non-empty list if the first card in the list has the same color. And color is going to be a symbol in this case. Here you can see I'm actually using the selector for color. So if the first symbol of my list is equal to the first symbol of my UNO card is equal to the color I'm looking for, then I produce true. There's no point in looking at any other cards in the list because I have a card that I can actually play. My next one is checking the value. So if the color doesn't match, maybe the value matches. And my value is going to be a natural number. So I'm going to compare, and here I am using the selector for the other field. Now, a lot of you are probably sitting there and wondering, why didn't I combine these two questions into a single case? And you could have done that. I could have said, if the symbol is equal to, if the color is equal, or if the value is equal. So I could have combined them into one and put it on one line. There's a reason why I didn't. Here's the problem. If I have some compound Boolean expression, or I have this or this, and that's my whole question, and I put it on one whole line, let's suppose there's an error in the code, be it a syntax error or a semantic error, some kind of problem with that line. Because I've put a bunch of expressions as this big compound thing on one line, it's very difficult for me to actually identify which part of that expression is causing the problem. So by breaking this up and putting it on separate lines, I actually make it significantly easier to debug. It's your choice how you do it, but I'm just explaining the reasoning behind my own implementation. Now, we've got the case for there's no cards. We've got the case for color is equal, and we've got the case to check for a value equal. If none of those questions evaluate to true, then the current card is not playable, and we need to look at the rest of the list. So in our recursive case here, we are simply going to call playable card on the rest of the list, and color and value just go along for the ride. So there you go. That's all we needed to do. Now, let's actually give this a test. So before we do that, I don't like to actually do structure or list definitions down here in the interactions window. I actually prefer to define constants to do my tests with. And you are totally allowed to create constants in your code for testing purposes. I highly recommend it. It'll make tests a lot easier to write. So I'm going to define hand to be a list and we'll put some cards in our hand. There we go. Now we run it. I'm going to make this window down here a little bit bigger so you can actually see what's going on. And now we can actually do some tests. Now I'm not going to do all of the tests that you need to write, but obviously we need to do a test for when the list is empty. We should do a test for when we have a card in our hand that matches the color. We should do a test for when we have a card in our hand that only matches the value. And we should do a test for when there are no cards in our hand that match either values. There are more tests that you should do, but that's the basic test we're just going to do here. So we'll start with passing an empty list. Of course, the empty list produced false, so we're fine there. Now let's try for a card that's not in our list. It doesn't match. Yes, I know I spelled yellow wrong. Nobody said I could spell, okay? So we're going to try now for a test where the color doesn't match and the number doesn't match. So I'm going to do yellow 6. Not in our hand, produces the expected value. Now we'll do one where the color matches but not the value, which is still a playable card. So we'll do green, and then we'll do 3. So yep, we get our expected result there. And now we'll do a card where the value matches, but not the color, which it also produced true. There we go. We got our little function. Any questions about what we've done here? All right. Well then, if you have a clicker, get it out. There we go. So I'll give you a minute. This one. All right. Let's see where you got. Great. Most of you chose A. A is the correct answer. So the other ones are not correct. Obviously, E is not correct. E is you went away somewhere crazy for reading week and you drank way too much and don't remember where you are. hope you had fun. But the reason why B, C, and D are not correct is because of the word destructor. There is no destructor. Now, some of you may be familiar with this term, and some of you may not be familiar with this term. Essentially, here's the thing. Everything you create takes some amount of space. You make an integer takes space in memory. You make a list takes space in memory. If you take memory, you probably want the ability to give that memory back. So when we create a structure in many languages like C and C++ and Java, we have to request memory, and then we usually have to give that memory back when we are done. And there is an explicit command in order to do so. There is no such command created by define struct. Racket takes care of the memory for you. So it detects when you are done with something and it deletes it on your behalf. That is, it returns the memory on your behalf. And that's called a garbage collector, and Rackets is actually quite sophisticated. So there are no destructors here. There are a constructor, you get some selectors, and you get a predicate. And now, technically speaking, there's a few other things you get. We're not going to use them because they break the rules of pure functional programming. All right, so let's do another one then. When you're looking at this question here, the context is if you were going to do a tracing through the execution of a program, what would be the substitution rule? That's what you should be thinking. What's the substitution rule? Does this behave like a built-in function or not? All right, let's see where everybody fell on that one. The answer, by the way, is yes. If you actually go back to earlier in Module 10, and we show you the substitution rules for all of the wonderful functions that are created for you by structures, you will see that they actually behave like built-in functions in that so long as you pass them a value, you get the answer immediately. So if I call uno-color on an Uno card, it in a single substitution step will give me the color. So it is behaving like built-in. All right, one more. You only get 30 seconds for this one, though. All right. Let's see where everybody falls with that fun one. A few people aren't sure what midterms are or are confused by the fact that you have a midterm. I understand the sleeping responses. All right. Obviously, you have a midterm. I believe it's Monday of next week. Now you've got me confused. I actually have multiple midterms next week. So next week for most CS students is called Hell Week. It's a special Hell Week for me. So I get to deal with multiple ones. There is a midterm. It is next week. You should seriously consider studying for it. How should you study for this midterm? One of the things that I highly recommend is going back over your assignments and maybe redoing them. I know you don't have a lot of time for that. Nobody's got time for that. Another thing is, I've actually, if you haven't already seen it, there is a sample midterm that I created that is posted to Piazza along with solutions. I can tell you that it looks a lot like your midterm because I wrote both, and I tend to be lazy when it comes to designing question types. So what is the coverage of said midterm? The midterm covers everything up to and including the end of module 9, which was recursion. So accumulative recursion is fair game, but structures not so much, which is good, right? Because you just started them. On that note, many of you would probably like some additional help, I assume, with studying for the midterm. So our ISAs have ever so graciously volunteered to give up weekend time to run a thing I'm not supposed to call a review session. Apparently I'm supposed to call it a help session. It's a review session. There will be a post made to Piazza probably today or later tonight to figure out what is a good time on Saturday or Sunday to run this little session. And so if you're planning on going home to your parents or your significant other or your dog or your cat or, I don't know, your game console, maybe this isn't a good weekend to do that. And how the session is probably going to go is you will have opportunities, of course, to ask questions, but we're also going to present to you some questions and give you an opportunity to try them. So you're going to be presented with extra sample problems. And on that note, if there's a particular topic you would like more sample problems on, please send me an email within the next 36 hours, and I'll make sure that you get a few more sample problems for those particular topics before the midterm. Yeah. And if you're wondering, what wonderful things do I get to take into my midterm with you? You get to take yourself and like a pen or a pencil and your what card. There are no cheat sheets, there's no reference sheets, there's no calculators. We're actually going to be posting the first page of the midterm to the course website, so you'll have an idea of what's expected of you. So no surprises. Hey, at least it's not the fall term. In the fall term, there are 2 midterms. You guys only get 1, right? I think that's fun. One other thing I do want to mention, it's very important that you remember that in order to pass this course, you do have to pass the weighted average of the midterm and final. So please do take the midterm very seriously. All right, any questions about it? Aside from, I'm sure I'll like, just tell us the questions that are on it. I can't do that much. All right, then. So before we get back into talking about Module 10, a couple things to... Yep.
I think last week you said actually
That might be true. I don't remember. Yeah.
Could you, are we required to know every single thing that he's telling the PPQ, or we just need to know what you taught in class?
It's like you want to know whether you need to know everything in the slides and in class.
Or just in class?
Generally speaking, I only hold you accountable for things that I have explicitly taught in class. Because I usually make the assumption that nobody reads the slides. But that being said, we do follow the slides mostly close. Yeah. I'm not going to expect, now I've taught more than what's in the slides in some areas, like when it comes to order notation, that's not on there. I'm not going to ask you to prove any big O stuff. That's like second year CS. So don't worry about that. No, it's CS135, not CS240 or 145. Do you want to prove?
No, well, you really do that.
I mean, will you be expected to trace through some code step by step? Yes, but that's not a proof. That's just being a human computer. Yeah, no proofs. This isn't a proof course. Neither is my other course. No proofs. All right, so that being said, don't forget assignment 5 is due today, and no, you're not allowed to use structures on it. And assignment 6, I apologize, it took us a little bit longer to get out than we anticipated. I had a bit of a hard time working on it over reading week because my laptop was in the shop getting repaired. It's repaired now, and now we don't have any extra C's, which is great. But assignment 6 is now released, so you can look at it. Yeah?
What's the assignment 5 to day like 9 p.m.?
9 p.m. That was a mistake apparently on Marcus. I was not aware of that. Assignments due at 9 in the morning, that's inhumane. It's March 10th? I don't know when March 10th is. It's March 10th. Yeah. We're not going to give you an assignment due like the day after your midterm. Like, that's cruel and unusual punishment. Or at least I'm not going to claim that other people won't do it, but I'm not doing it. So Hell Week is already bad as it is. We don't need to make it worse. Not only do I get to proctor 2 different midterms, I get to mark them. No, it's not. All right, so assignment 6 is out, and now I know you're probably going to be very tempted to ignore its existence in lieu of a midterm, but my recommendation to you is to actually read through it. There are less questions than you're probably expecting, but they are a little harder, and it's good to have those problems just ruminating in the back of your brain as you're doing other things, so that when you actually have time to sit down and do A6, your brain's already been thinking about it subconsciously, so do read it. Yes, it's a Pokemon-themed assignment. I apologize for the Pokemon fans out there. I probably broke like all the game rules. Pokemon came out when I was in like high school, so I never really got into it. My daughter loves it, but she tells me I play it wrong, so all right. All right, so we left off, we were talking about structures, and in particular, we were dealing with this problem in Racket of mixed data. So we've done an example already of how define struct creates for you this lovely structure, and then you get all of these functions for free, which is super awesome, because if you did this with a list, you'd have to make those functions yourself. So define struct kind of does it all for you. And now you have this lovely named thing in your code, and that's really nice too. But one of the problems is sometimes data isn't simple. For example, students. There are undergrad students and there are grad students. And then there's also this thing called a postgrad student or postdoc. They're kind of this weird hybrid thing. And what might come as a surprise to you is many undergrad courses are actually attended by both grad and undergrad students. So in particular, my CS135 course actually has grad students in it. And the reason why we have grad students taking undergrad courses is because sometimes we have grad students coming from, I don't know, like film studies, and they decide to join CS because everybody wants to join the dark side, right? And so they need to build up their CS background, so the school requests that they take 341 and 350. So here's the problem. Grad students have different fields than undergrad students. They share a lot in common. They have a name. Everybody has a name. They have a program, and they also have a list of classes they're enrolled in. But grad students actually have extra things. Grad students have supervisors. They can actually have more than one. And obviously an undergrad student doesn't have that. So how do we create a function that can accept students of type undergrad and of type grad student? So realistically, what you want to do is you want to create a structure of type student, and then have a structure of type undergrad and a structure of type grad student inherit from it. So they get everything from student. And that would be called, things like polymorphism. And Racket does not have this. So we can't do that. Instead, what we're going to have to do is we're going to have to create a structure for an undergrad student, a structure for a grad student. So we're going to create the structures for the specific types, and then we create a data definition to mix them together. So structures for the undergrad and the grad student, and then we create the data definition for just a student. This is what it looks like here, and then we'll create another data definition for a class list, which is just a list of students. Now, if you're looking at things like polymorphism and inheritance, as I said, this isn't really something that we do with Racket. But this is something, if you're a C++ or a Java programmer, you're probably already familiar with. And if you're not, CS246 is going to ram that down your throat. That's a fun course. I like C++. All right, so once you've created these two different data definitions and these structures, you need to actually create a template for a student. And the template for a student, and I think I showed you this last class, is actually going to take the templates from an undergrad and a grad student and kind of combine it together. Because a student, a function involving a student, well, you are going to have to access the fields of this undergrad student different from how you would access the fields of the grad student. So you have a condition where you use the predicate to check if it's an undergrad or grad, and then you put the templates for using the different selectors for each of those. And now that we've got this lovely, lovely template, we can actually go through and we can write some functions, like maybe you want to change your program. Because maybe you're in geomatics, whatever that is. I keep hearing about it on Reddit. Seems to be the butt end of every joke. Apologize if you're in geomatics. If you are, please send me an email and tell me what the hell this program is. Maybe you're in geomatics and you've decided to join us in the dark side of CS. So we've got to go through and we've got to update your program. So if you look at this, we've taken the template and we say update program. If you're an undergrad student, we're going to make a new undergrad student, because remember, we can't modify existing data. We can only make new things. So we're going to make a new copy of you where your program is now CS. And if you're a grad student, we'll make a new grad student where the name is the same, the supervisors are the same, but the program's been updated. Just following the template here. And we can do other functions. I think we looked at them before. For example, we can have a class list of students. Remember that a student is a data definition, it is not a structure. And in our class list, we want to find everyone in the room who is a geomatics student, and we'll give them 100% automatically for being in a program that I have no idea what it is. All right, so I need to filter, I need to find everyone in geomatics. So I'm going to go through my list, and you'll notice here we've actually made use of a helper function. And that helper function is in program, because I don't want to put all of the logic of checking whether you're an undergrad or a grad student and calling the appropriate selector here. I want to keep my recursive function as simple as possible, but I also recognize the fact that checking what program a student is in may be useful elsewhere. So I create that function as a separate helper because I might use it. And then I'm going to check if you're in the program, then I'm going to add you to the list, and if you're not, I just move on. Super, super simple. All right. Now, one last thing about contracts. So we have shown you the contracts as using the structure definitions and the data definitions, so student and undergrad and grad student. And that is the way that you should aim to do it, because it's going to give you the most readable and simplest contracts. It isn't, however, the only correct way to do it. So if we wanted, we could replace student with this syntax here in our contract, any of undergrad or grad student. Of course, a class list, which is a list of students, would then become list of any of undergrad and grad student. Nobody wants to write all that crap. Even though it is totally valid, you should really stick to using the names that you define in the data definitions and the structure definitions. They're both right, though. All right. Now, we have a little problem. And to show you this little problem, I'm actually going to go back to Racket. And I just want to clear this up a little bit. So we've got this UNO card definition. Now we know mentally that color is going to be a symbol, and we know that the value of the card is going to be a number. But what is stopping our idiot users from passing peanut butter sandwiches as the color and VCRs as the value? Absolutely nothing. Because when we make the structure, you'll note that we don't actually specify what the type of any of our fields are. And the only time where we would actually run into problems is, let's say, we tried to add two colors together. And if the field values were not numbers, then of course Racket would throw in an error. But, you know, I would really like it if I could protect my users from being stupid. You should never assume your users are smart. Users will always do the strangest things. I always use the example of my cousin who put a peanut butter and jam sandwich in the VCR. Never expect that your users are going to be smart. So what we want to do is, because the constructor provided by defineStruct doesn't actually validate the types because it doesn't know what types the fields should be, it would be nice if we created a checked constructor. So a special constructor that's going to take the arguments that we need to create the structure and validate them according to what type we want them to be and make sure the values are in the correct range. Because I don't want to be doing this. Because right now I can do make uno and I can have a list be the color and a string be the value. There's no stopping me from doing this. So this is not something, by the way, that Racket gives you. They don't give you this checked function. But if we wanted to create a safe constructor that's going to validate the name and validate the student's program and validate the class list as being the correct type and the correct lengths, then we can create this checked constructor. And what we're going to do is we're going to check to make sure that the name is a string and that the name is greater than 0 characters, because we could just as easily pass in an empty string. And even though it is a string, I don't know, does anyone in here have the name of an empty string? I think our database would actually break that was true. So I also need to make sure that your program name is a string, and I need to make sure that your program actually, has more than 0 characters, so it needs to be at least a blank one. And I need to make sure that the class list is a list. And it can be an empty list, because maybe you're not enrolled in any classes, because maybe you're on co-op. So I check all of these things, and only if all of these tests pass, then do I actually call the real constructor. Otherwise, I'm going to produce an error message to indicate, hey, you've tried to create a student with some invalid arguments as its field values. This, again, is not something that Racket gives you. And if you are creating a program that you're anticipating users are going to be using, you should seriously consider making checked functions. Never assume that your user is smart or reads documentation. I mean, think about it. If you're downloading a program, if you're installing Apple's latest update, do you read the EULA? Nobody does. I can't think of a single person who has ever read an EULA. So don't expect that people are going to read your documentation either. All right. Any questions about that stuff so far? Okay. So one of the last things to kind of mention is you might notice that there's a lot of similarities between structs and lists. There are a lot of similarities. In fact, if I were to go and implement defineStruct, I would just use a list to implement it. And that's probably actually how it's implemented in Racket anyways. We can actually do lots of things with structures, and we can do the same thing with a list. What are the advantages and disadvantages of using the struct versus the list? Well, obviously, one of the advantages of using the structure is the fact that you can define struct, and it gives you a constructor, and it gives you the selectors, and it gives you the predicates. So you don't have to do anything. It gives you all of the basic functions that you need, and the nice thing is everything is neatly named. If you try to create your data type as a list, however, you don't get those functions, and you're going to have to implement them yourself. Now, a bonus of you having to implement them yourself is that you could implement them by default as checked functions. Whereas with the struct, since the ones that are given to you are not checked, you would then have to, if you wanted checked ones, you'd have to go and rewrite them anyways. Now, there are some other advantages and disadvantages here. Some of the big ones are that lists are more generic. So structures make more readable code. They save you a lot of time and effort, but they are very specific. You can only use those functions for that specific data type. And if you create your data types and functions to work on lists, they may actually be more generic. And generic means it works more on more than just one kind of type of data. So there are advantages of using lists. I can tell you that in my own Racket code, well, it's scheme code, and you might be thinking that I actually use scheme outside of this class. Yes, I do. The GIMP, which is the GNU Image Manipulation Project, I don't remember what it stands for. It's the Linux version of Photoshop. You can write plugins in either Python or Scheme. I hate Python, so I use Scheme. And if you're sitting there thinking, she hates Python, oh my God, what are you, weird? Python is a white space sensitive language, and white space sensitive languages irritate me. That doesn't mean I don't know Python. I actually know Python pretty well. I just don't like it. I don't like a lot of things. All right, one last thing I want to talk about. So we were able to take you from using cons to create a list to using list to create a list, which was really nice. We called it a list abbreviation. There's one more level of abbreviation we can go to, and that's the quoted list. And that's, if you ever see me making lists in my own code, this is how I do it. Essentially, what I do is, instead of creating this nested list as list red, list blue, green, I put a single quote out front, and then I just do red, blue, green. And this is equivalent to this. What's interesting is the quote actually gets applied to everything on the inside. Now, everything? No, it's going to check to make sure, okay, is this actually a function name, or is this something that we don't have a definition for, and should I turn it into a symbol? So it does do basic syntax checks like that, but it creates this really nice short form for creating a list. And it's really, really awesome. Now, how it behaves is a little bit different. So what's interesting is that not only can you create lists in this way, but you can actually create numbers and strings, and you can actually quote them. So I can actually do this. Now, you might be thinking these two things are symbols, but they're not symbols. What's actually going to happen here is the next step. These aren't symbols. I'm going to look at this and I'm going to see quote 5. And I'm like, oh, I need to evaluate that. Oh, that's a number. And so I get replaced with 5. And then I look at the next one. Oh, that's quote 5 as well. Oh, that's a number. And then we can evaluate the function. So essentially what we're doing is we are going to just delay the evaluation of the thing that we've quoted. So quoting is really, really powerful. Now, why would you do this? I don't do this. This is silly. Very, very silly. The only time and place that I ever use the quote notation is when I'm being lazy, creating a list. That's the only thing I do it for. Now, technically speaking, what ends up happening is, so I do this, and what this is really, helps if I can spell, and then when I try to get the first of the list, it will then turn that back into a number. So it behaves really weird. All right. But yes, as of now, you can use quoted lists, right? Just not on the midterm. Yeah. It's good to know them, but I don't, unless I specifically ask like a question on the final exam, convert this quoted list to a regular list, I don't care if you use them in your code. I would anticipate from assignment 6 outwards that any of our sample code uses quoted lists out of sheer laziness. Because when I'm writing code or writing anything, it's a question of what is the fewest number of characters I can type. All right, so any other questions about structures, quoting? Yeah. Well, it's sitting in this form here, it's not evaluated. So Racket doesn't even know yet. So the only time where it would actually try to figure out what that object is if we tried to do something with the first of the list. Then, if we got first of the list and tried to add it to the second of the list, when we actually tried to evaluate the add, it would then have to convert that back to a number. You can consider it as the quoting is kind of delaying evaluation.
So if I use a string append, will turn this into a string?
If you use string append, why would you use string append here? It's a bunch of symbols. I don't think string append works with numbers.
So it doesn't detect what that thing might be, or how you use it, and then turn it to type it out.
No. All right, any other questions then? Okay, it is time to start a new topic. And it's module 11, by the way, which is posted. And this is probably one of the most important topics in computer science. Well, important data structures. So, the data structures that you have so far, you've got basic atoms. So those are simple data types like numbers, characters, symbols. And then you've got compound data types like lists and structures and strings. And we started talking a couple modules ago about abstract data types, which are the building blocks which we can build more data types which are suited to doing certain problems in good amounts of time or just good at representing certain kinds of data. So we had lists, which are an abstract data type technically. We had association lists, which are also an abstract data type. And we had dictionaries, which are another abstract data type. Trees are probably one of the most important data types out there. And this is something that, whether you realize it or not, you have probably been using since the day you started using a computer. For example, the files on your computer are stored, well, they're not actually stored, but the searching of those files is actually done as a tree. So your disk has a root. Now, if you're a Linux user or a Mac user, the root is actually called root. It's the slash. And if you're a Windows user, the root of your disk is C:. And then underneath that, you have a bunch of directories. And then inside those directories, you have other directories and other files. And if you want to find a file on your computer, you start at the root. And then you're like, oh, I need to find a program I downloaded. So on my Mac machine, I would go to the root directory, and then from root, I go to users, because I want something in my download directory. And then from users, I go to my username, and then from my username, I go to downloads. That file system, all of those files, actually forms a tree known as the namespace tree. And that is actually how you find things. Now, they didn't always exist like this. Back in the 50s, it was just everything in one big directory. Or if you're 5 years old, it's everything in one big directory, right? But that's a tree, and that's a tree that you have been using probably since you started using a computer. But trees are everywhere, not just, the ones outside. For example, binary expressions can actually be drawn as trees. And essentially what you do, a binary expression, by the way, those are operations that take 2 arguments. So add, subtract, multiply, divide. So if we take this expression here, we're going to take the first operation, which is the division, and its arguments are the left side and the right side. And so I make the operator, the node, the root, divide, and then the left side will be everything on the left side of divide, and the right side will be everything that's on the right side of divide. Now I keep saying side, what I actually mean is left child and right child. And then for the right child, I see I have 2 times 6 plus 5 times 2. So splitting that again into left and right, I put 2 times 6 over here on the left and 5 times 2 on the right. Yes, I may have left and right confused. Oh well. So binary expressions. You can take most basic math expressions and actually represent them in this tree-like structure. Other places where you can see trees are anything to do with biology, like doing, genus classification, evolution trees, looking at, the amoeba, it evolved into a chicken in this particular path. That's a tree. Other places where you might think are trees are family trees. not quite. Because family trees can get very complicated, and things like your brother might also be your mother. And I'm from a small town, okay? This happens. I won't get into details. Trees are everywhere, that's the point. Yeah. So, technically speaking, a tree is a network, because a tree is a graph. But a tree is a very specific kind of graph. There are rules about trees. So normally what we do is we have at each node can have one parent, and it can have any number of children. But we'll get to the rules in a minute. All right, so trees are everywhere. So now let's talk about some of the terminology with respect to trees. So first off, we draw a tree as a bunch of nodes, and those nodes are connected by edges. Now every tree has one and only one root node. Nodes can have a parent, but only one parent. This isn't human trees where you have two or more parents. This is, worm trees where you only have one parent. You cut the worm in half and now there's two. I don't know if that's actually how it works. So every node can have at most one parent, but nodes can have as many children as they want. There's only one root, and the root node has no parent. It's the origin of the species. Now, some other interesting things about trees. Trees are connected. That means there are no nodes that are just sitting out there in space all by themselves. Trees also do not have cycles. What that means is that I should not be able to start at the root and go down to the bottom and then somehow manage to find my way back up to the root. There should be no loops like this. I can't go like this around in a circle. Now, we call nodes at the top the parent, and any node that is below you, directly below you, is going to be your child. So you are the parent, and you may have some number of children. Your children may have children, which become your grandchildren. If your grandchildren have children, those are your great-grandchildren. Siblings are the other children of your parent. We don't usually get too much into siblings. Now, there's different kinds of nodes. So there are internal nodes, and an internal node is any node that has at least one child. And then there are leaves, and a leaf is a node that has no children. And if you think of a tree outside, there aren't like branches growing out of the leaves. They're at the end of the line. So leaves have no children. Now what's interesting about a tree is you can usually take a circle, like draw some region around it, and that creates for you a subtree. So starting at some other node, and you take some part of that tree below it, that's a subtree. Now you might be wondering, what if my tree has one node? Is that technically connected? Yes. A tree may have only a root node, and a tree is still valid if it's empty, because it's connected, because there's no nodes, and there's no cycles. We also talk about ancestors. Those are the things that came before you. So your parents, and your grandparents, and your great-grandparents, and your descendants are everyone that is your children and below you. And then what's interesting is that we can label or attach data to different parts of a tree. So it's most common to see data attached to the nodes. And in particular, we may attach data to each node. It's also exceptionally common to see data just attached to the leaves. And I've even seen trees where data was only attached to internal nodes. I've also seen trees where data was attached to the edges, but that's less common. All right. So let's play a game then. And just to get you used to the concept of trees, for those of you who have not seen it. of you say that is a valid tree? How many of you disagree? Nobody disagrees. Anyone confused? A few people? All right. This is a valid tree. It has one node, and only one node. It has no children. It is the root. It's totally fine. How many of you say that's a valid tree? Anyone disagree? It is a valid tree. What else is this tree? This tree is also a list. It's kind of fun, isn't it? All right. How many of you say that's a valid tree? Does anybody disagree? Why is it not a valid tree? And most people who think this isn't a valid tree, you're thinking about a binary tree where we say that each node can have at most 2 children. We're not talking about a binary tree, we're just talking about a tree in general where we can have any number of children. So that is actually a valid tree. No problem there. Yeah, eraser thing. All right, how many of you say this is a valid tree? How many of you say this is not a valid tree? This is not a valid tree, but there is a special name for this. It's called a forest. And you might think that's funny, but that's actually the truth. A forest is a group of trees. So this is technically a group of trees. Now, what about that? How many of you say that is a tree? How many of you say that is not a tree? That is not a tree because there are cycles. This is a graph, which is just a bunch of nodes that are connected to each other in any way we want. Now, technically speaking, all trees are graphs. All trees are graphs. But not all graphs are trees. So trees are a subset of them. Yep. Are forests graphs? Yes, because the definition of a graph does not require connectivity. That's a fun one. All right. So, just a couple things. So, internal nodes, those are nodes that have at least 1 children, and a leaf is a node that has no children. Remember that you have only 1 root, and a root has no parent. And also remember that labels can exist on all nodes, or just the leaves, or just the internal nodes. So there's a lot of flexibility on where we can attach a label or a piece of data. And the other thing you might wonder is, does it matter how we draw the tree? Like, could I draw the root down here or the root to the side? No. That doesn't matter if we drew it upside down. It's still a tree. It's about the properties, not about how you've actually drawn it. The other thing is the order of the children. For a generic tree, the order of the children does not matter, but when we start talking about specific types of trees, this may change. Any questions about this so far? Yep. Yes. Yep. They would count as labels. And in fact, probably in 2 or 3 or 4 lectures, we will actually do that very example with code, which is kind of fun. All right, any other questions then about the general idea of a tree? All right, so then, as it turns out, there are many, many different types of trees. And this is something that if you stay in computer science, or you switch into computer science, or you're already in computer science, you're going to be covering trees until your ears bleed, because we cover them in 136, they get covered in 240, and so on and so forth. It's a very important data structure. Now, as I said, there's many different kinds of trees. So the kind of tree most people have heard of is a binary tree. And a binary tree is just a tree where each internal node has at most 2 children. So you can have no children, you can have 1 child, or you can have 2 children. 0, 1, or 2. Then there's a variant of that called a binary search tree, which is super, super useful. And then from a binary search tree, there's some unfortunate negative effects of a binary search tree, which we can improve upon in a special kind of binary search tree known as an AVL tree. And then there are also things called red-black trees. And then we also have some super fun trees we like to use in computer graphics. They are the quad tree, the oct tree, and the KD tree. And I'll tell you a little bit about those, even though you'll learn about them in 240. What essentially they do is in computer graphics, let's say I wanted to render this room, and I wanted to ray trace. Essentially what I need to do is all of you would be represented by a model made up of millions of little triangles. And I have to send a ray of light through each pixel of my image and figure out which triangle from all of you billions of triangles do I actually hit. And the problem is, if we store all of those triangles in a long linked list, that means I have to query potentially every single triangle. Well, not potentially, I do have to query every triangle. So what we do with the quad tree and the oct tree and the KD tree is we actually use the tree structure to subdivide the space. So for example, everything to the left and everything to the right. And then I take everything over here and I divide it into 2 again. And I take each one of those subdivisions and I keep subdividing it further and further into halves. And then my query, my ray of light, instead of having to try intersecting with each of you, I notice, oh, the ray is on this side of the room. So I go down this side of the room. And then I notice the ray is here. So I go down here. And then down this subdivision. And I end up having to intersect significantly fewer triangles than what I did before. So before, the order was linear time, and when you use one of these oct trees or these quad trees or these KD trees, you get log n instead of n. So it's significantly better. So in computer graphics, these spatial division trees are huge. There's also B trees, there's R trees, there are range trees, so many different kinds of trees. I'd like to show you one that you have seen in action, but probably never known it was there. It's cool. It's probably my favorite kind of tree. It's called a trie. And if you're wondering, T-R-Y, no, it's called that, trie. And I'll give you a very simple example of it. I'm going to compress it a little bit. So, one place where the trie tree is used is when you go into Google and you go to type something into the search bar and you start typing words. And it brings up a bunch of suggestions for you. How does it know what to suggest to you? This tree. So let's suppose you started to search for CS135 midterm. So when you type CS135, you moved from the root of the tree down to this node because you matched in CS135. And now Google sees there's options midterm, A1, A0, it sucks, it rocks, is, to continue. And then you type midterm. So you go from here in the tree, and then you go here. And then for midterm, it might suggest to you the answers. Or it might suggest to you, Easy Ace has all the things. Or maybe it suggests to you a cheat sheet. Or whatever. you typed CS135 midterm, and because of the path you took through this very special tree, it was able to suggest to you things that people had typed. So every time somebody types something, Google records that in this tree, and then it can suggest to you completions for that. Now you might be wondering, why do you get different completions from your friend? Because obviously there's probably billions of possibilities here, and it usually chooses the one that matches your profile closely. So there's more going on with Google's math than that. This is a really cool tree called a try. You'll learn lots more about tries in CS240, but I love them. They're super fun. All right. So we're going to talk about binary trees and binary search trees. So we're going to keep it pretty simple. So, as I said a few minutes ago, a binary tree is a very small subset of trees, and it is the set of trees where each node has at most 2 children. And usually how we refer to the children is you have a left child and a right child, because if we were to draw it, we'd draw it where you have one on the left and one on the right. And that's really all there is to a binary tree. It's a tree where you have at most 2 children. There's lots of different ways that you can draw a binary tree. So you would normally see binary trees drawn like this, where you have your nodes with their labels and then just edges between them. But let's suppose now I actually want to create this data type inside a bracket. I want to make a structure. How would I think about what that structure needs to be created as? Well, what I would do is I would use this other method here to try to figure out how do I create the structure. What I notice is that each node in my binary tree has 3 components. The first component is the data, the value at that particular node, a key, a label, whatever you want to call it. Then I have a left child, and I have a right child. Those children might be empty because I might be a leaf, or they might exist. And from this definition of a node, this little picture here, I can actually figure out what the data structure should actually look like. Now you might be wondering, why did we call it a node and not a binary tree? Well, each of the individual nodes in my tree are not, we don't call them trees, we call them nodes. But we don't have the ability in Racket to create a structure for tree that contains the structure for node. That doesn't work. So what we're going to do is, just like we did with students, we're going to create the specific type in each specific type. So I'm going to create my node type. So my node has 3 things, the key, and the left and the right. And then my binary tree is actually just a data definition. So that's what it is. That's it. Now I need to create a template. And if you go into the slides, you'll be like, wait a minute, it's blank. Okay, we'll open Racket and we'll do it. So, let's go close off our clicker stuff there. And let's create a new tab. So, first off, we're going to need our structure. There we go. And now we can create our template. So, takes a binary tree. Okay. A binary tree can be empty. It's totally valid for a binary tree to be empty. We should do something when the binary tree is empty. If the binary tree is not empty, then I probably want to do something with the current node's value, that is my current root's value, and then I may want to do something with the left child, and I may want to do something with the right child. And specifically, I may want to relate the value at the current node in some way to the results of looking at my left child and looking at my right child. So with those thoughts in mind, we could actually create a template here. So there's our base case. Otherwise, we're going to do something with the value at the current node, and I'm going to combine that result with the results of looking at my left child and the result of looking at my right child. Now you notice I kind of used recursive language here because we're using recursive language here. because looking and working with a binary tree, presumably our template function or our functions related to binary trees need to visit every node in the tree. So you start at the root, and in order to visit every node in the tree, you have to recurse down your left, and you have to recurse down your right. Each time, you have to go to the left, and you have to go to the right. So that's what we're going to do. So we're going to combine the result of looking at the current node's key with the results we get from recursing and looking down our left subtree and looking down our right subtree. And of course, don't forget to put all the appropriate ... dots in there. There you go. This template here is showing you how to actually visit every single node in the tree. Now you might be wondering, well, how do I know to stop visiting my children? Well, if you have no children, then in your structure, we'll use the empty to indicate there's no left child or no right child, in which case we would hit the base case when we called the BT template on an empty child. So it does stop. By the way, some would call this kind of recursion structural recursion because our path of recursion, or the way that we recurse, is following the way the structure is actually defined. All right. So now we've got a template fleshed out. We should do something with this tree. Very basic function to start with. Maybe instead of storing all of our numbers in a list, we have decided to store all of our numbers in a tree. So maybe we want to sum the numbers in our tree. In order to sum the numbers in the tree, we need to visit each and every single node in the tree, which means I need to add the current node's key to the result of summing all of the nodes in my left subtree and all of the nodes in my right subtree. I'm going to follow my template. So this, again, is not in the notes. So we'll go over here, and let's actually implement this. Pretty much copying straight from the template. If the binary tree is empty, then we have nothing to sum, and therefore we should produce 0. So that's our base case. Otherwise, we are going to add the value of the current node to the sum of the nodes in my left subtree and the sum of the nodes in my right subtree. Remember that the plus operator can take more than 2 operands. All right. There. Oh, I can't spell. I'm going to assume that's what you were putting your hand up for. Nobody ever said I could spell very well. All right. So now that we've got this function, we should make a tree. And again, this is one of those cases where it's very helpful to make constants to do your testing with. I'm going to call it tree because I don't know what else would I call it. Make node. I'm going to run out of space very quickly here. So remember that if we don't have a child, we use empty. So if there's no left child, you put empty in the constructor. And if there's no right child, you put empty. So there, I have a tree. It contains 5, 4, 3, 2, 1. And I know that if I sum up these numbers here, that I should get 15, right? We can do adding. So there we go. We hit sum, and we get our expected value of 15. Now, a base case is when the tree is empty. So we should also be able to call sum on empty. And if I call this on a single node, should give me that value. It's pretty cool, right? All right. Now, one last thing before we go today. If you're sitting there looking at this template and this implementation of sum, and you're still quite confused as to how it works and how it visits every node in the tree, my recommendation for you is to start drawing a few binary trees and actually trace the path that it's taking through that tree so that you can see exactly why we end up visiting all of the nodes in the tree. Sometimes I find with tree problems, it's a lot easier to figure them out by actually drawing a tree and experimenting with it. So that being said, I'm going to leave it there for today. And you can use these extra 3 minutes to, finish assignment 5 or maybe start studying for the midterm. Or go home and eat supper.